Section 3.10, all about word problems. So now you get your wish. You want to know where we're going to get to use this stuff. Here's a few problems where you get to use that, and yes, you get to have some of these on your test as well. Anytime I'm going to solve a word problem, the first thing I do is draw a picture. They've got a lovely little picture here of an oil spill. I'm not going to attempt to draw it because they've got a pretty one there. They've got a little procedure here. I guess I do follow those steps. I'll let you read through those and you can follow them. First thing I do is draw a picture. I don't think they say draw a picture, but that is the first thing I do. The next thing I do is I read through the problem and I try to write down some of the information. They tell me that the radius of the oil patch is increasing at a rate of 30 meters per hour. I know that the radius is changing at a rate that implies derivative of 30 meters per hour. This means the radius is changing at this rate. They'd like to know how fast the area is increasing. They want to know this. How is the area changing with time? And specifically, they want you to then come up when the radius is 100 meters. All right, pretty important equation that I know about this one. Pi, area equals pi r squared. I'm going to need that. Just to get an idea of what's going on, let's look at the 0 hour. At the 0 hour, the radius is 0 and the area is 0. At hour 1, the radius is going to be 30 meters because it's changing at a rate of 30 meters per hour. And that implies that the area is going to be pi times 30 squared, or 900 pi meters squared. At hour 2, the radius is going to be 60. The area is going to be pi times 60 squared, which would mean 3,600 pi meters squared. So this area is changing at a different rate. Well, let's figure out how it's changing. Here's my formula. I betcha I could just take the derivative of both sides with respect to time, remembering your implicit differentiation. So I'm going to take the derivative of both sides with respect to time. So derivative area with respect to time is pi is a constant, and really all you've got here that's any sort of function is just r squared. I know what the derivative of that is. That's 2r. I'm using implicit differentiation, and r is a function of time because it does change with time, so I do need to leave this dr over dt just like we did in implicit differentiation. Oh, here I have the equation for how area is changing with time. It's just 2 pi r times however the radius is changing with time. Okay, so if I want to know this, when the radius is 100, just plug it in. 2 pi times 100 times, and the radius is changing at a rate of 30. This is going to be, when you crunch the numbers, 6,000 pi meters squared per hour. Note that this was in meters per hour. The 100 is in meters. Oops, if my little M will right there. So there is my answer. If they want the decimal approximation, I can just crunch this on my calculator and I get something like 18,850 meters squared per hour. But if they want the exact, here's the exact answer here. Here's the approximate. Once again, they have a nice little picture here. I'm probably going to draw my own, but I put these up here for you. Two small planes are approaching an airport. Here's my airport. One's flying due west, so he's going this way at 120 miles per hour. The other one is headed due north, 150 miles per hour. I'm going to say that they're approaching this airport, so that rate is closing in and those distances are getting smaller. So I'm going to be giving, because those rates are changing, so that both, I'm going to call this X and I'm going to call this Y. So both of the X and the Y are getting smaller at those rates. That's how those distances are changing. Then this distance here is going to be how far they are apart. I got to give it a letter. I don't like to give things D, although I kind of want to because it's the distance, but then once I start dealing with derivatives, then I've got these two D's going on and it gets ugly. So this is going to be the distance that they are apart. I know that at a particular point in time, at just this snapshot, they're telling me that they want to know when the westbound plane is 180 miles from the airport and when the Y plane is 225 miles from the airport. They want to know how fast is the distance between the planes changing. They want to know dz over dt. They want to know how fast the rate is changing. It helps to write down these X's and Y's and figure out what these things are. This 120, this negative 120, that is how the X is changing with time. So let me write that down. This negative 150, that's how the Y is changing with time. So I'm going to write that down as a rate. I can get this Z. I'm going to do a squared plus b squared equals c squared. So that's going to be the square root of that 180 squared plus 225 squared. And this Z value is going to be, let's see, I've got it over here, 288.1 or so miles. So let's write down the relationship that I have. I know that x squared plus y squared equals z squared. I'd like to know how this relationship is changing with time, so I'm going to take the derivative of everything with respect to t, remembering my implicit differentiation because both x, y, and z are changing with time. So this x will be 2x, and the x is changing with time, so I need to remember that, plus 2y, and the y is changing with time, equals 2z, and the z is changing with time. Now I notice that these 2's really don't even matter because there's 1 in everybody. I'll divide everything through by 2 just to get those suckers out of there. And I can start replacing with some numbers. My x at this point in time is 180. My dx over dt is minus 120. And we can put in units, if you will. And this 180 is in miles, plus the y is 225 miles times the 150 per hour equals the z we calculated to be 288.1 miles, and the dz over dt, that's what we want to know. So when I do the algebra of this, you know, just crunch this number, crunch this one, and then divide everything through by the 288, you will get dz over dt oops, yeah, the dt is about negative 192 miles per hour. Why is it negative? That's because this distance is closing in with time, meaning that depending on whatever time it is that you're looking for, this distance is closing in and getting smaller and smaller, so these z values are getting smaller with time. And there's my airplane problem. All right, sand pile, very typical kind of question. Sand is falling from an overhead bin and it's making a cone. And very important note here, radius is always 3 times the height. Let me just write that down. Radius is always 3 times the height. It's a cone. Area of a cone is volume equals 1/3 pi, and then it's r squared h. The sand is falling at this rate, so this is some sort of derivative. It's falling at that rate. I noticed the feet cubed, so if I was a bit concerned about what it might be, I noticed feet cubed is a volume, so the dv over dt is falling at a rate of 120 feet cubed per minute. So that's how that volume is changing with time. How fast is the height changing? So they want dh over dt, and specifically they want it when h is 10 feet. Alright, so we're sitting here with this formula. The volume is 1/3 pi r squared h. They tell me that the radius is 3 times the height. I really want to know about dh over dt. Don't really care about the radius, so I'm going to chunk in, and they did this as a great big favor to us, 1/3 pi times 3h. I'm going to substitute that in for r so I can have everything in terms of just h's and v's, because that's what I really have information about. So volume is 1/3 pi, and that's 9h squared h. Cleaning that up just a hair, volume is, that would be 3 pi h cubed. Okay, now that's clean. So let's look at taking the derivative of both sides with respect to time. Get me a new color here. Let's do this in green. Derivative of volume with respect to time. Derivative of both sides with respect to time. This is just a constant, so that'll come out front. I'll have dv over dt equals 3 pi. Take that derivative of that height because it is changing with time. That's going to be 3h squared. I'm using implicit differentiation, and height is changing with time, so I need to remember to include this dh over dt. Alright, I can clean this a little bit. I can just call that 9 pi if you want. H squared dh over dt, and this is dv over dt equals that. That's really pretty. Now here's what I'm wanting to know anyway. I want to know that thing right there, and I want to know it when h is 10. So I'll just substitute in my numbers. dv over dt is 120 feet cubed per minute. 9 pi, I need to know it at 10 feet. This is going to be quantity squared times dh over dt, because that's what I want to know. And crunching this around, I'm going to get that dh over dt is, let's see, that's going to be 120 feet cubed per minute times 9 pi times 100 feet squared. Notice my units. And if you would like to know what this is exactly, it's going to be 120 divided by 9, let's see, 3 will go into both of those. That would be like 40 feet over. And let's see, and 3 went into that, 3 pi minutes. And let's see, I think that I forgot a 0 in there. Hold on. I did. I forgot 2 zeros in there. So forgot about that 100. So there is what he looks like. It would be 4 over 30 pi feet per minute. Crunching those numbers, you'll get 0.042 feet per minute. And that would be how the height is changing with time if the sand is falling at that particular rate. And that's my sand problem. Last step, we got a hot air balloon. Groovy little pictures here. I'm going to draw my own just so I can walk myself through this. An observer stands 200 meters from the launch site, so here he is. And he's 200 meters from the launch site, and that value doesn't change. He doesn't walk closer. That the distance from the launch site is always the same. The balloon's going up though, so I have a dy over dt. Oh, and they give that to me. That's 4 meters per second. And they want to know how fast is this theta changing with time. So they want to know d theta over dt, specifically when t equals 30 seconds. Alright, so let's look at this y value here. I see I have a triangle. So at t equals 0 seconds, y is 0 meters. At t equal 1 second, y is 4 meters. T equal 2 seconds, y is 8. I don't really care about any of those, but I do care about t equal to 10 seconds. And at 10 seconds, y is, that would be what, 40? Alright. Oh no, I care about 30 seconds, sorry. Let me do another one. Okay. So I have this relationship. This is just a regular right triangle. Theta, how does theta relate to this opposite and adjacent side? Oh, that relates with a tangent. So tangent theta is y over x. Now this y is changing, but the x is not. So I'm just going to go ahead and chunk in what x is, because he does not change with time. He is always 200, so he's static. I'm going to take the derivative with respect to time so I can get this d theta thing going on. The derivative, and it's going to be with implicit differentiation, so the derivative of tangent theta is going to be secant squared theta d theta over dt equals, this is a constant times this y, I'm taking the derivative there, that's going to be 1 over 200 just dy over dt. And I'm looking for d theta over dt. Oh, and they gave me dy. I know that little guy right there is just 4. Okay, and that always is a 4, so I'm just going to go ahead and replace that. So let's look at d theta over dt, solving it. That's a 4, so that'll reduce a little bit. That'd be 1 over 50, I guess. 1 over 50. Dividing and getting that secant squared over here. So it would be secant squared theta. I guess I could rewrite that as cosine theta over dt equals, how about cosine squared theta over 50? Well, that looks pretty good so far. Now, at that 30 seconds, y is 120, x is 200. Ooh, I could probably tell you what that theta is because I can do this. Theta happens to be, I want to know what the cosine of that theta is, so that is opposite over hypotenuse. I could do that a squared plus b squared thing, and if you do, you'll end up getting 233.24 meters here. So I would then in turn get, this is all over 50, so it'd be squared, adjacent. Sorry, cosine is adjacent over hypotenuse. That's 200 over 233.24. And if I crunch those numbers, I'm going to end up with 0.015. And theta in this case will be in radians per second. And that will be how that angle is changing with time. Rate of 0.015 radians per second. If you'll notice, I still drew my pictures anyway. The pictures are what do it for me. I draw my pictures and I start writing down not just numbers, but what those numbers relate to in terms of the variables. And whenever it's a rate, I write it down as that dy or d theta or dv or whatever it is. Write that down with respect to what is changing. And if you need any help with these, you know where to find me. See me at the Collaborate or email me. You can even text me on the telephone. Bye now.